Welcome. Today we will be talking about the coffee ball mill. This is Team 2 and my name is Matthew Rule. Also on the team is Nate Deaton and Hassan Al-Nasser. We are representing the University of Nevada, Reno through CHE 415 particle technology. So let's get started. Now the goal of the project is to create an operational ball mill that can grind whole roasted coffee beans. We're going to quantify our results through particle size analysis and solution density. The particle size analysis will be done through mass distribution, and solution density will be measured through optical density. So why coffee? As you can see from this flowchart, for an engineer to make a solution, there has to be a problem, and it could be any problem. But additionally, coffee is needed for any solution. An engineer needs coffee. So this is a coffee life cycle. We'll be focusing on the grinding of the coffee and the brewing of the coffee. So why a ball mill? A ball mill uses high density balls to crush particles. It is a very simple design and it is very effective. As you can see from this little video, the ball inside the ball mill will be thrown against the opposite side of the wall, crushing any particles within. So ball mills in industry. They are usually used for size reduction, often in mining for processing of ores. It is also used in the coal industry for reducing the size of coal. It is additionally used in blending of explosives, which is wet milling, but today we'll be talking about dry milling. Now, one of the most important designs of a ball mill is the critical speed. The critical speed is the speed at which the ball mill will essentially act like a centrifuge. Critical speed is calculated through the equation 1 divided by 2 pi times the square root of g divided by big R minus little r. G is the acceleration due to gravity, big R is the radius of the drum, little r is the radius of the ball. Now in industry, the rotational speed of a ball mill is usually chosen between 65% and 85% of the critical speed. As you can see from these three graphs, the middle one, which is slightly below the critical speed, will do the most crushing. The balls and particles are brought up through the side of the wall and crushed on the opposite side. If you're too slow, the balls stay at the bottom of the drum, and if you're too fast, the ball mill acts as a centrifuge. Now, for our design, we used a PVC pipe which is 6 inches in diameter and 8 inches in length. Our calculated critical speed was 2 rotations per second. We chose 1 rotation per second, which should be roughly 50% of the critical speed. And we chose that so there's crushing and our ball mill would stay intact and not take too much damage. I will be now passing it off to Nate, who will be talking more about our design of the ball mill.
Hello everybody, this is Nate Deaton. This is the Team 2 Particle Technology Project. In this video I'm going to be talking about the components of the ball mill and how they operate. So, starting with the base of the ball mill, this is the structure we use to hold the drill. These 3 screws right here used to hold the base of the drill when the ball mill was in operation. So you just stick the drill in here like that, and then you just turn it on. And then one design requirement we had to do is we had to have a clamp right here on the drill trigger so it could operate at constant output. And then moving on to the next component was the top of the ball mill. So this was the drill bit piece that we used to actually operate the rotational speed of the ball mill. We would stick it in here, and then we would glue the top into the top of the ball mill lid, and then that would require that would operate the rotation of it, so forth. And then moving on to the base of the ball mill, this is what the base looked like. We had these 2 bottom axles that the actual mill would sit on and use to rotate like that. And then the drill would be attached to the head, which would be attached to the bit, which would then operate the power and then constant output of the rotation. And then this was what the base looked like. The copper tubing right here is surrounded by the PVC pipe for a frictionless rotation device. And then moving on to the last portion of it, the inside of the ball mill. To create the balls to actually rotate, we use this little orthogonal piece that would create friction so the balls can move up and then operate at a critical speed. Alright, so continuing with the design of the ball mill, we use 25 steel ball bearings with a 1-inch diameter, and this is what they look like right here. High density used to crush the coffee beans within inside the mill. So starting an experiment, we would take the ball mill, pour the ball bearings inside of the ball mill, and then moving over to the scale of the coffee beans. We say that it's weighed at exactly 50 grams for consistency purposes. And then we grab it, like so, pour it down in there like that. And then looking on the inside of it, this is what it looks like with the bearings inside. Okay, after we pour the beans into the ball mill, we proceed to set up the equipment for the experiment.
Now, while Nate's setting up this experiment, I'm going to be talking about safety. Safety is a key factor to this experiment. Now, while the ball mill is running, all team members and anybody around must be wearing safety glasses. Additionally, there are many pinch points while the ball mill is operating, so we must wear industrial gloves while it is operating, and this is just to ensure safety of us and anybody around.
So, as you can see, this is what the setup looks like for the ball mill. This is the mill, this is the spade bit, this is the drill, this is the power. This right here is the mount for the drill, as explained earlier. And then this is the rotational device that the mill rotates on. So, showing how it would work, we would usually have a clamp right here to create constant power output for the ball mill. But to show a little demonstration, I'm just going to pull the trigger on it. So it looks like this.
Now for data collecting. I'll be passing it off to Hassan to talk about mass distribution and to Nate to talk about optical density.
My name is Hassan Al-Nasser. In this part of the video, I will show you the method of how to use the sieving machine to find the mass distribution. And here we have a layer of the sieving that we are going to use, so the particles will fall through this, and hopefully we will find the mass distribution after that. Right now we have the sieving machine right here. So as you can see, we used like 5 sieving layers used for particle analysis. So basically what it does, it shakes the particles, and the smaller particle, if we have a smaller particle than the mesh, it will fall down. So we did a runtime of 15 minutes, and at the end of the process we weighed the coffee grounds at each sieve to get the mass distribution. So right now I will show you how this machine works. So it's just like this, and basically the smaller particle will fall down and we'll get the mass distribution after that.
So additionally, along with the mass distribution results, we used a digital refractometer to measure the optical density, or the concentration of the solution at each sieving layer. So depending on the runtime and the surface area of the distribution, what you would do is put the sieving layers in an aqueous solution, and then you would extract it using the pipette, and then you would just stick it onto this surface right here, and then you would just push read, and then that measures the optical density. And what we found from the results, as explained later by Matt, is that the concentration increases with a longer runtime due to the leaching process that we observed.
Now to our results. Anytime during this video, you're welcome to pause the video and take a better look at our data, as I will be going through this section pretty fast. Now if you look to the left, Tyler mesh, that is our sieve size, and to the right is mass, and mass percent for each runtime. I'll move on to this graph because you could see the data a little more reasonably. If you look at the purple color, which is the 10-minute mark, it shows that the majority of the mass is at the 0.63 millimeter size. If you look to the left, the purple bar is much smaller. It tells you that the majority of the particles are small. From this, we could calculate average diameters. Now, the average diameter of a coffee bean is 6 millimeters. After our 10-minute runtime, the average diameter of the particles were around 1 millimeter. That is a very large reduction in particle size and proves our mill was working. Now this chart shows optical density versus surface area. If you look to the left at the orange mark, that is the optical density of water. And then to the far right, the blue mark is the optical density for our 10-minute runtime. Now this is an approximately linear line, and it tells you that as surface area increases, optical density increases. Optical density meaning a stronger cup of coffee after brewing. In conclusion, we had a very successful project. The ball mill was able to crush coffee beans relatively easily and effectively. Now thank you for watching our video. If you have any questions, you could leave a comment down below. We would like to thank and acknowledge Dr. Cornella, Mike Kvistic, and Dr. Med. Without them, this project would not have been possible. Thank you again for watching the video.